Well, hello and welcome to our journey into algebra and number theory, and we were up to this section in the chapter on congruences. We've been looking at linear congruence equations, and I'm just going to tuck in here the rather lovely result which follows on quite naturally from the concept of a unit that we discussed before. So a unit, remember, is an element which has a multiplicative inverse in Zm, and the set of all such elements with multiplicative inverses U sub m, as we've seen, forms a group. This is called Wilson's theorem. Apparently it has nothing to do with Wilson, but was attributed to him by Euler, probably in fact not written in this form, but probably goes back to Fermat. Fermat didn't have the modular arithmetic notation. That didn't come till later with Gauss, but he may well have understood, expressed in his own terms, this particular result. And it's one of the few theorems in number theory that says P is prime if and only if something. In other words, you could actually take this to be a definition, or this fact here to be a definition of a prime number. Moreover, you might have, let me just say what it says. So if P is prime if and only if, when you work out P minus 1 factorial, that is, you multiply 1, B2, B3, B4, all the way up to P minus 1, if you divide that number by P, the remainder is always minus 1. Now, at first glance, one might think, this gives us a lovely test for primality. If I give you a number and say, is it prime? Well, you just check whether this is true. If this is true, then the number's prime. However, of course, you quickly realize that the numbers here get big very, very quickly, and that this is in fact not a particularly practical way of checking whether a number is prime. It does, however, have some quite important theoretical implications that we'll look at a bit later on. So this is called Wilson's theorem. The proof of it is fairly easy, in fact. I'm only going to do one way. If P is prime, first I'm going to prove that if P is prime, then this is true. So if P is prime, then the group of units is equal to just Zp star, that is all the numbers from 1 up to P minus 1, and we're excluding 0 in that list. So we take an element A in this one, then A has an inverse because it belongs to the group of units. So if A happens to be its own inverse, which is possible, then I can multiply both sides by A, and I get A squared is 1 mod P. That means that A squared minus 1 is divisible by P. I can factorize this difference of two squares. So P divides A minus 1 times A plus 1. Now, because P is a prime, if P divides the product of two numbers, it must divide one or the other. That's because of the primality of P. That means P divides A minus 1 or P divides A plus 1. This one here says that A is congruent to 1 mod P. This one says A is congruent to minus 1 mod P. And minus 1, of course, is the same as P minus 1 mod P. So the only numbers in this list that are their own inverses are 1 and P minus 1. So apart from those two objects, apart from those two elements, apart from 1 and P minus 1, every element of Zp has an inverse different from itself. So when I write down this P minus 1 factorial, which is 1b2 up to P minus 1, every number except the first and the last, every number in here cancels with something different from itself. And so after all the cancellation's gone on, all that survives is 1 and P minus 1, and that's congruent to minus 1 mod P. The converse is simply says that if this is congruent to minus 1, then P is prime, and that's fairly easy to prove. I leave that for you to think about. So another little example for you to try is to do the following to show that follows easily from that one. is to show that if p is a prime bigger than 3, then 6 times p minus 4 factorial is 1. And that's a pretty easy exercise to do. I want to say a little bit more about groups, and we're going to look in particular in the next section more closely at the structure of Zm and Um. And to do that, we need a little bit more about group theory, a little bit more theory of groups in order to study the structures of these two sets. So in the earlier section on rings, we defined this angle brackets A to be the set of all integer multiples of A, that is plus or minus 1 times A, plus or minus 2 times A, and so on, whenever A was in the ring. Now, that was when our operation, we were thinking here of the operation as being additive. So since our group operation in UM is multiplicative, I'm going to define angle brackets A to be the set of powers of A, 1A, A squared, A cubed, and so on, for A in the group, where G is now a group. If the group turns out to be nothing other than this set, this square brackets A, then we're going to say that A is a generator of the group. And if A to the n is 1 for some positive integer n, then this group, angle brackets A, consisting of the powers of A from 1 up to A to the n minus 1, this is called a cyclic group of order n, and is written as C sub n. So C sub n simply consists of, you take an object we're going to call A, and this Cn consists of all the powers of A up to A to the n minus 1. One can also have the infinite cyclic group. If we think of n, take a limit as n going to infinity, then the cyclic group C infinity simply consists of A, 1A, A squared, and so on forever. But for us, we're going to be only considering finite groups. So just as a little example here, if we take Z star 11, now 11 is a prime, so Z star 11 means all the numbers from 1 up to 10. We're leaving out 0, of course, and that is just every element in that set has an inverse because 11 is prime. So that's the group of units here. And it turns out that if we take the number 2 and work out the powers of 2 modulo 11, so 2 squared is 4, 2 cubed is 8, 8 2s are 5 mod 11, 5 2s are 10, 10 2s are 9 mod 11, 9 2s are 7 mod 11, 7 2s are 3 mod 11, 3 2s are 6, and 6 2s are 1 mod 11, and look, you actually get all the numbers 1, 2, 3 up to 10. This is in fact U11. That means 2 is a generator for this group U11, and U11 is a cyclic group. In other words, it's a cyclic group with 10 elements in it. On the other hand, if I try to do the same thing with the number 3, then it doesn't quite work, because 3 squared is 9, 9 3s are 5 mod 11, 5 3s are 4, and 4 3s are 1. We don't get all of U11. We get a cyclic group now with 1, 2, 3, 4, 5 elements. So this is a cyclic group of order 5, and it's not equal to U11. So in this case, 3 is not a generator, but 2 is a generator. Obvious questions arise here. Do these U groups have generators? What sort of U groups have generators? How do we find a generator? How many generators are there? All of these very interesting questions we'll have a look at in a later section. Notice, by the way, that 2 to the 10 is 1. If I calculate 2 to the power 10 mod 11, I get 1. But 3 to the 5th gives me 1 mod 11. And we say that 2 then has order 10, and 3 only has order 5. In other words, 10 is the smallest positive integer that I need to raise 2 to get 1, and 5 is the smallest positive integer I need to raise 3 to get 1, and we're going to call that the order of the element. So here's our definition. Given an element G in a little g in a group capital G, the smallest positive integer n, so that g to the n is 1, is called the order of G. Now also we're going to say the number of elements in a finite group G is called the order of capital G, and it's written as these absolute value signs around G. Now be careful to distinguish between these two uses of the word order. The order of an element is the smallest power you need to raise that element to get 1. The order of a group is simply the number of elements in the group. So again, let us just play around with U11, and we've seen that this set generated by 3, 1, 3, 4, 5, 9. These are the powers of 3. These actually forms a group in its own right, as you can see from the multiplication table. And now it starts to get interesting. So we write down these elements. This is 3, 3 squared, 3 cubed, 3 to the 4th. And if you write out the multiplication table of these, modulo 11, you'll notice again it's a Latin square. Every number in this set appears exactly once in every row and column. And so this set here is a group inside a larger group, U11. And we're going to call that a subgroup. So a subset of a group G, which is itself a group, is called a subgroup of G. And we're going to use this notation H is less or equal to G to denote that A is a subgroup of G. So from now on, when I read this, I'm going to say is a subgroup of. So H is a subgroup of G. Notice, of course, G is always a subgroup of itself, and the identity element is always a subgroup of that group. Just as example here, if we take U24, these are all the numbers that are less than and relatively prime to 24. That's 1, 5, 7, 11, 13, 17, 19, and 23. And we can list just by hand some of the subgroups here. So 1 and 23 forms a subgroup. 23, multiply 23 by itself, you get 1. So this is closed under multiplication, and so this forms a subgroup. 1 and 5 forms a subgroup because 5 squared is 1 mod 24. And similarly, this is another subgroup, 1 and 7, because 7 squared is 48, which is 1 mod 24. 1 and 13 forms a subgroup, and so on. If we look at U21, these are the numbers less than and relatively prime to 21, 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19, and 20. Then again, just by hand, one can calculate some subgroups of this. 1 and 20 is a subgroup because 20 squared is 1 mod 21. 20 squared is 400, which is 1 mod 21. The set 1, 2, 4, 8, 16, and 11, this also forms a subgroup, it turns out. If you multiply any of these together, any two of these together, and read it mod 21, you stay inside the set. 1, 4, 16 turns out to be a subgroup, etc. And there are lots of other subgroups as well. However, let's just enjoy what we're seeing here with this. In particular for U21, this subgroup has got 2 elements, and U21 has got the number of elements in this divides the order of the group. This has got 1, 2, 3, 4, 5, 6. U21 has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the size of U21 is 12. Let me write this over here. So the number of elements in U21 is equal to 12. So we've got a subgroup here, it's got 2 elements. 2 happens to be a factor of 12. This set has 1, 2, 3, 4, 5, 6. This subgroup has got order 6, which happens to be nicely the factor of 12. This subgroup has got 3 elements, and 3 again is a factor of 12. And so we feel a theorem coming on here. So in each case, the number of elements in the subgroup is a factor of the number of elements in the original group. This result is one of the most fundamental facts about groups, and it's called Lagrange's theorem, named after the French mathematician Lagrange. So Lagrange's theorem says for finite groups, the order of a subgroup, that is the number of elements in a subgroup, divides the number of elements in the group, divides the order of the group. And the proof of this is not that difficult, but we'll just quickly go through a little proof of this. So suppose we have our subgroup H is a subgroup of G, and G contains n elements. The size of G is n. So you take your H, and I'm going to list the numbers as, well, firstly I'm going to call the first one 1. It's going to be always in the subgroup, so I'll call that H1. And I'm going to suppose there are R elements in this subgroup called H. So I'm going to take this and I'm going to multiply it. I'm going to pick an element G, any element of G you like, and I'm going to multiply each of the elements here by this G, and I'm going to call this G times H. So GH means you multiply every element in this by G. So G itself is in there because G times 1 will give me G, and that's GH1, all the way up to GHR. Now, by the way, if the element G that I pick here happens to also be an element of H, then of course, because H is a subgroup and it's closed, if I pick an element G here that belongs to H, then GH will in fact just be H again. So just observe that there. The elements, now this set is called a left coset of H, is the technical name for this. And I claim that the elements of this set, these numbers, these objects here, are all distinct. Since if you've got 2 of them that are the same, then because you're in a group, you can multiply both sides by G inverse, and you get HI equals HJ. And that tells me then that the elements of this coset are all different. So we start off with R different elements, and we end up with R different elements over here. None of them map to themselves. Also, I claim that these cosets are all distinct. That is, if I take F and G in capital G, and I make F different to G, then FH intersect GH is empty, or, so there's either nothing in common or everything is in common. There's either nothing in common, they have an empty intersection, or the 2 cosets are in fact identical. So how do we prove this? Well, if it's not empty, then there is something in the intersection of these, and that means there is an FHI equals GHJ. So there's some object that belongs to both of these. If it's in F capital H, it must look like FHI. If it's in G capital H, it must look like GHJ for some I and J. I can then multiply both sides by H inverse, and I get F H inverse H J inverse is G, but this object here is just an element of the original subgroup H, so that says FH is G. And if I now multiply the subgroup H by these elements, then I get G times H is FH times H. But of course, because H is in capital H, little h times capital H is just an element of capital H, and this is just F times that one. So that tells me that either the intersection of these is empty. If it's not empty, then the 2 cosets were the same. Now, since 1 belongs to my subgroup, every element of G has to belong to some coset, and hence the set of cosets chops up or partitions G into the size of G over the size of H, sets of equal size, and that means the size of H is a factor of the size of G. Now, that's a slightly more difficult proof, but that's a little proof of the Lagrange's theorem. So just as an example, the group C6, the cyclic group of order 6, has subgroups 1 and 3. 1 and a cubed, which has got 2 elements, or 1a squared a to the 4th, and this is a subgroup of size 3, and both these numbers 2 and 3 are factors of 6. And just to finish up with a little corollary here, the order of an element G divides the order of the group. So that's a very nice fact as well, that the order of the element divides the order of the group. And the proof of that is easy. We simply take our element G, we take the set, the group spanned by that one, the group generated by that one, call that H. H is a subgroup of G, and so H divides G. But of course H is the smallest element n, such that G to the n is 1, but that's precisely the order of G. So as a final example here, in U sub 10, the numbers in U sub 10 are 1, 3, 7, 9, and these elements have order 1, 4, 4, and 2, that is 3 to the 4th is 1 and nothing smaller, 7 to the 4th is 1, nothing smaller, and 9 squared is 1, all modulo 10 of course. And these numbers are factors of 4, which is the order of the group. And in the next video we'll finish off by having a look at the applications of these ideas back into number theory when we have a look at Fermat's little theorem and Euler's theorem.